Hi there, this is Peyman Bateni joining in from Vancouver to present our work on enhancing featured image classification with unlabeled examples. This is the work that we have the privilege of showcasing at WACV 2022, and it's been my privilege to collaborate on it with Barber, Dr. Jan-Willem and Dr. Frank Wood. I'm sure you're familiar with visual classification, conventional visual classification, I should add. We have 1,000+ images per category, lots of data. We spend hours training on high-intensive GPUs, and eventually we get a classifier that presented with an image gives you the right label. In featured image classification, our goal is to reduce the amount of data we need considerably. We are dealing with 1 to 20 images per category, and we also add an amortization step, which is we want to produce a classifier within a short period of time that still, when presented with an image, can accurately describe what it is. Specifically, in this visual learning setting, we have a set of tasks where each task comes with a support set, which is a set of labeled images, images and labels, few of them, 20 or less per category, and a sort of query images for which these are unlabeled images and we would like to produce the right label for. Now, in this work, we focus specifically on transductive visual learning, where we assume that that query set of images, the unlabeled images we hope to produce the labels for, are given all at once. So specifically, the contributions of this paper is as follows. We present transductive CNAPS, a new method expanding on our earlier work, namely simple CNAPS, that uses a two-stage transductive task encoder and an iterative soft k-means procedure for refining class parameters to achieve state-of-the-art performance on the more difficult multi-domain Meta-Dataset benchmark. We additionally, despite the method having not been designed for these benchmarks, achieve very competitive performance on mini and tiered-ImageNet, including state-of-the-art performance when we use a more feature-rich, more data-rich trained feature extractor. Lastly, we also theoretically ground our work in Bregman soft clustering. So simple CNAPS, which our work builds on, consists of a feature extractor with film layers, that is feature-wise layer and modulation layers, inserted across it. And those parameters are manipulated using an adaptation network that conditions on a task embedding based on the support examples. At the classification step, the said feature extractor, once adopted, produces feature vectors for each of the support examples that are then pushed into mean and covariance estimates to define class clusters for each class present in the task. In transductive CNAPS, we expand simple CNAPS through two major modifications. First, on the feature extractor, we update the task encoder to leverage both the support examples, those are the labeled examples, and the query unlabeled examples in a transductive manner. So we have this hierarchical mean pooling step followed by a two-step LSTM that produces the final task embedding. At the classification step, we furthermore, at test time only, expand on simple CNAPS by using soft labels on the query images to further refine cluster parameters. That is, we have this iterative refinement algorithm that at each step first assigns soft label probabilities to each query example based on the current cluster parameters, and then follows back in the second step and uses those very soft probabilities to update the cluster parameters at hand. This results in major performance improvements on the Meta-Dataset benchmark. We see strong performance to the state-of-the-art level, even compared to more recent benchmarks overall. But specifically, we see a considerable gain on out-of-domain performance, suggesting that this transductive refinement actually improves generalizability to out-of-domain tasks. Additionally, we show that on the mini and tiered-ImageNet benchmarks, transductive CNAPS achieves the state-of-the-art on 4 out of the 8 settings considered, while producing competitive or matching state-of-the-art results on the others. Now, we additionally consider the case of introducing a more data-rich feature extractor, and we see that using that transductive CNAPS is able to achieve state-of-the-art across the board. Thank you for listening to our presentation. Our paper is available on arXiv and will be available in the proceedings, and we've released all code on our GitHub. Thank you.